This is 5-4. May the 4th be with you. 5-4-15. And we're going to talk, this is chapter 12, obviously. We already did all the crystalline solid stuff that we're going to do, so we're not going to visit those again. But we are going to talk a little bit about liquids. And most of this we can do in about 3.5 seconds because you know it from like the 7th grade. Liquids have a definite volume but no definite shape, unlike gases which have neither definite volume nor shape. They have less kinetic energy than gases, but more kinetic energy than solids. And stop me if you've seen this before. I know you have. That's a joke. Solids, liquids, gases, and we could do P for plasma. And this is just, increasing kinetic energy of phases of matter. We have to add energy to get something from a solid to a liquid. We have to add more energy to get it from a liquid to a gas. We have to add a whole bunch more energy to get it up to a plasma state. So the attractive forces in a liquid, so talking about liquids here, are pretty effective. They do hold stuff together. So the attractive forces between particles work really well because these things aren't moving so fast that they shoot right past those attractive forces. They've got good internal cohesion. Those particles are going slow enough that the attractive forces do hold them together, and so they move in a... Liquids are considered one of two states of matter, which are a fluid. The other one is gases. And a fluid is anything that is able to flow, anything that takes the shape of its container. That's about all we can say about that. There just aren't fixed positions like you have in a solid. Okay, so we know that liquids are more dense than gases. They have a higher density. We even measure it in different units. So in gases, if you remember, we tended to use things like grams per liter for density. Here we would do grams per milliliter or grams per cubic centimeter for a liquid because they're much more dense. There is much more mass per unit volume. For the most part, we can't compress them. And I say that with some reservation. There are liquids in which we can get some amount of compression, but it is minuscule. It's very, very tiny. Often what looks like compression of a liquid is compression of gases trapped within a liquid. So you have a solution of a liquid with gas in it. Can anybody think of an example of a liquid with gas trapped in it? Pop. Yeah, carbonated beverages. It's a liquid that's had carbon dioxide shoved into it. And so it looks fairly compressible, but really what you're doing is compressing the carbon dioxide. You're not compressing the liquid itself. Liquids diffuse, just like we talked about in gases, and we see surface tension in liquids. We see it especially in water. We'll talk more about water later. So at the surface of any liquid, there is a force that holds all of the molecules together, and that's what allows us to float a pin on a glass of water. That's what allows things like water striders. I was just out catching water striders Saturday. All the things that skim on the surface of water. That's permitted because there is this surface tension that almost creates like a thin film. It's not a solid, but it's certainly got more attractive force than the rest of the body of the liquid. And capillarity, we love capillarity, though we don't have a lot of time to talk about it. We have an attraction. So if you imagine reading your graduated cylinder, what is that thing that forms at the top, that little dip? Meniscus. Why does the meniscus form? Because at the surface, so here's our graduated cylinder, and here's the surface of our water. At the surface of that water, if we took a close-up view of the inside there, each of the water molecules over in this side is being attracted to the side of the container, to the glass. Those water molecules are all being attracted to the side of the glass, and these water molecules are all being attracted to those water molecules. So it ends up pulling up along the side. So the meniscus actually happens as a result of capillarity. Water is especially prone to capillary action. If you dip the edge of a piece of cloth into liquid, what happens? It climbs up the liquid. That's capillary action. Because what's actually happening is the water molecules are climbing up tiny narrow channels in the fabric. This is how paper towels work. Okay, so now we're going to talk about the big thing, phase changes. We will talk about phase change diagrams a little bit later in this chapter, but right now I just want to make sure, and again, I think from like the 5th grade you're all good with this, but the change from a liquid to a gas we call vaporization. Notice that it's not called boiling, and it's not called evaporation. That's weird. I thought it was evaporation. I thought it was boiling. Why is it not? What's the difference? Don't know yet. Okay. Both boiling and evaporation are special cases of vaporization. Okay? They are both special cases of vaporization. We're going to talk a little bit more as we go. Oh, it's right there. Never mind. Whoops. Evaporation means that all the particles are coming off the surface. Okay, so if we leave a glass of water out on the table for a week and it's all dried up, all of the liquid particles that went into the vapor phase escaped from the surface of the liquid. If we put a pan of water on the stove and we boil it, particles from the center of the water, so we'll make this a clear pan, so particles from down here in the water are escaping the surface. They're hurtling themselves at the cliff, which is the surface of the water, and flying out into the vapor phase in the air. And that's how we get a cloud of steam over a pot of boiling water. You can, if you wish, have homework tonight of going home and boiling water and watching it. It's actually kind of soothing, sort of meditative, perhaps. It'll also curl your hair. Okay, so we have vaporization. We have the two special cases, both evaporation and boiling. And we can call going from a liquid to a solid freezing, or we can call it solidification. Solidification sounds more impressive. Freezing is what we're accustomed to. But if you say, have the ice cubes in the trays solidified yet? Rather than, are they frozen yet? Your family will think you're really clever. Two phase changes we didn't mention. So if we have solid, liquid, and gas, we said going that way was vaporization, and going that way was solidification. So those are all leaving the liquid state. What do we call it if you're going from a solid to a liquid? It's not a trick question. Melting. Yeah, there's no fancier term for it. Well, you can say liquefaction. You can say liquefaction. But we typically just call it melting. And what do we call it if you go from a gas to a liquid? Condensation. Yes. So let me move that guy over there. So that would be condensation. There's just two that we haven't covered. So who knows one of these?
Sublimation.
Which one is it?
From a solid to a gas.
Yeah, straight from a solid to a gas is sublimation. Anybody know gas straight to a solid? I'll let you look that one up. That'll be a challenge. I'll tell you what. I'll make it a half-point bonus. Come in with that on a slip of paper tomorrow. No, email it to me. Email it to me by tomorrow. So going directly from a gas to a solid. Half-point bonus. Yeah, 1-point bonus in the homework category. Okay? Email it to me. Okay, so we know a lot about solids. We're not going to talk a lot about them now because we've pretty much done what we're going to do with them. They're more closely packed. They have lower kinetic energy. They're solid. And we talked a little bit about these when we talked about crystalline solids. So we have crystalline and amorphous. Not much else to say. In terms of any solids, definite shape, definite volume, definite melting point. So what happens at the melting point? You add enough energy that they can overcome their attractive forces and start to flow past one another. Not enough energy to become a vapor and really just bounce off the walls, but they start to flow. Not dense, or not compressible, very dense. Try compressing a rock sometime. Go ahead. Try it. That's how we get metamorphic rocks, is compression of solids. But you don't really have the amount of energy that's required to do that. And very low diffusion rates. People are always surprised when I say that there is any diffusion rate for solids. There is a diffusion rate for solids. However, the time scale is like hundreds of thousands to millions of years. So if you clamp a piece of zinc and a piece of aluminum together and leave it alone for, I don't know, 500,000 years, some zinc atoms will migrate into the aluminum side. They will diffuse into the aluminum side, and some aluminum atoms will diffuse into the zinc side. But this is not like diffusion of gases or liquids. It's really crazy slow. So, but it does exist. There is a diffusion rate for solids. It's just crazy, crazy slow. Equilibrium. How many of you are familiar with what we will call colloquial use of the term equilibrium? Anybody here ever have dizzy spells? Get sick, get a fever, have an ear infection, you get dizzy? Okay. That would be described at a doctor's office, if not as vertigo, as a disequilibrium. So equilibrium is sort of a nice steady state. In chemistry and in science in general, we say it is, are you ready, a dynamic condition in which two opposing changes occur at equal rates in a closed system. It's not very helpful. So let's break this down. What is a dynamic condition? What does dynamic mean? Changing, yeah. If a system is dynamic, there is change going on in the system. Two opposing changes. So I'll give you a little situation here. We have an Erlenmeyer flask, stoppered, badly drawn too, with water in it. And for every particle of water that exists in this Erlenmeyer flask, there are some particles up here in the air that are also water vapor. So when we talked about, for instance, collecting gases over water, we talked about the fact that any column of air is going to have some water vapor in it. We would expect to have more water vapor in this flask than in a similar stoppered flask that didn't have any water in it. Okay? Because particles from this liquid water are actually escaping into the gaseous phase. So they're all bouncing around, and every now and then one of them hits the surface with enough energy to, in essence, break the bonds that are holding it down in the liquid phase. Well, up here in the gas phase, these guys are really bouncing around. They're moving. Well, every now and then one of them hits the surface of that water and basically hits it with enough velocity to push it into the water. Well, once it's in the water, guess what? All those attractive forces in the liquid hold it in place. So it gets trapped, in essence. So we have particles entering and leaving the water phase and the vapor phase constantly. So particles are going from liquid to vapor, particles are going from vapor to liquid, all the time. Boom, 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 boom. But they're happening at equal rates. So the number of particles we have in each phase doesn't really change. And I will get rid of this. Now this is all premised on the fact that this is a closed system. Okay? So that's equilibrium. We have some change that's occurring, but it's happening at a steady rate. So the change is occurring at equal rate. So the number of particles in the water phase and the number of particles in the vapor phase don't change over time. Okay, so we did a little bit of equilibrium work. But then we changed the conditions. So we changed the rules of the game. We heated the thing up. And when we did that, suddenly those rates of change were not equal for a while. What would have happened if we then just held it at a nice steady temperature? What do you think would have happened to those rates of equilibrium? So for a while we were doing 2 out, 1 in. So we were putting more molecules from the liquid phase to the vapor phase. What if we then just held it at a nice steady temperature? 1 in, 1 out, 1 in, 1 out, 1 in, 1 out. It would all settle back down. It would all settle back down. So that leads us to talking about phase change equilibrium. And this is basically what we just did. So in any liquid system, you have particles that are hitting the surface and they're making it into vapor. They're evaporating. But some particles are hitting the surface and condensing. They're rejoining the liquid. So we can shift that by taking a liquid plus heat. And if we completely heat it, what do we get? Everything is vapor. If we take a vapor and we completely cool it, so we get heat off of the system, we now have all liquid, plus a lot of heat that we've generated. You can actually pull heat out of vapor, and you can absorb heat. Anyway, we'll talk about heat sinks another time. What we show this as, it almost looks like a reversible reaction. When they're equal, when you've got the 1 in, 1 out, 1 in, 1 out, that's an equilibrium position. Okay? So these are not equilibrium. This is where we're heating everything and everything is turning into a vapor. This is where we're cooling everything and everything is turning into a vapor and we're collecting heat from the system because it's losing heat in order to become a liquid. This is equilibrium. So we have some liquid particles that end up going into the vapor phase and they absorb heat to do that. We have some vapor particles that go into the liquid phase and they give off heat to do that. And guess where the heat that's given off is reabsorbed? By the particles that are going the other direction. So it's just this nice little loop, and particles either give up heat or take on heat, and they jump from liquid to vapor or condense back from vapor to liquid. Okay. At equilibrium, those rates are equal. Okay. This is one of my 2 favorite chemistry concepts for general life lessons kind of things. Le Chatelier's principle. When a system in equilibrium is disturbed, it will attain a new equilibrium that minimizes the disturbance. What the heck does that mean? It means that whenever things get shaken up or shuffled up, you settle down to a new normal. That's what it means. So, not a one of you has had a life where you've had no periods of disturbance, whether it's moving, losing a loved one, breaking up with somebody, your dog ran away, it's a new school year, you went to a new building, whatever it is. You've had some disturbance in your life. Like, you have had some kind of disturbance. And for a while, there's a bunch of change going on with that, and things are really chaotic, and then you settle down to a new normal. And you're like, oh, well, this is the new normal. Okay. All right. I can do this. That's all Le Chatelier's principle says. Now, Le Chatelier's, of course, is not as philosophical as I make it out to be, but that's my own interpretation of scientific principles for everyday living. Maybe I should write a book. No, probably not. Because I've only got 2, and that's thin soup. We're going to actually watch a simulation of Le Chatelier's. So what we're saying with Le Chatelier's is that rate of change is going to spike for a while. So for instance, if we heated this up there, universal sign for bad flame. If we heat this system up, so we were at a point where we had liquid plus heat yields vapor. When we heat this system for a while, we're going to have a lot more particles heading this way, which means the way we express that is that we are shifting the equilibrium. So if this thing was sitting at 10 degrees Celsius before, and after we heat it up, it's sitting at 30 degrees Celsius. I mean, it's still not at the boiling point of water. You know, we haven't boiled all this water into vapor phase, but are we going to have more particles in the vapor phase now? Yeah. So we've shifted the equilibrium towards vapor. Once we turn that flame off, if we now hold it at 30, we will have more particles that are in the vapor phase. And they're going to go right back to one in, one out, one in, one out, keep changing places, but we've shifted equilibrium. So there are a lot of things we can do to shift equilibrium, and not all of them are intuitive. Okay, this is a whole lot of text. We're not going to talk about all of it, but the big idea is that when we change the conditions of a system, we shift the equilibrium. We can shift it towards liquid, we can shift it towards vapor. Okay? And, you know, anytime we change something, like if we double the temperature, suddenly more particles are escaping. But once we then hold it at that temperature, it settles down, we have a new equilibrium. In other words, everything settles down to a new normal. Okay. When we talk about it, we talk about shifting equilibrium left or right. You can imagine the nightmares this causes for me, somebody who can't reliably tell left from right and who gets very confused talking about my left and right and your left and right. So I tend to, though it is completely incorrect, and any good chemistry instructor would laugh at me heartily, I tend to say shifting towards vapor and shifting towards liquid, because I really do get confused. Sorry. When we heat the system, these are straight from your book, because believe me, I would struggle. Heating it shifts it towards vapor. Cooling it shifts it towards liquid. The volume ones are a little bit counterintuitive. If we take the vessel that we had and we make it into a bigger vessel, we put the same amount of stuff into a larger vessel, increasing the equilibrium will shift the whole system towards vapor because there is more space for vapor to exist. If we put it in a much smaller container, and therefore we lower the pressure on the surface holding molecules down. If we put it in a smaller container, we shift it towards liquid. And we're not even going to do adding and removing liquid, but these you should get familiar with. This is where we'll start tomorrow, but it's a really interesting idea, and once you get it, the aha moment is fairly powerful. So, where have you heard the term vapor pressure before? You did some lookups in chapter 10. What were you looking up? Water vapor pressure. So we were talking about the water vapor pressure. The equilibrium vapor pressure for any liquid we have in that closed system that we've been talking about. If the liquid and the vapor portions are in equilibrium, there is a given amount of temperature, or at a given temperature, there is a given amount of pressure that's exerted by the vapor. Okay? So when we looked at water vapor pressure, it was different at every different temperature. We had to look it up by temperature. So as long as the system's at equilibrium, so we're doing the one in, one out, one in, one out, there is going to be a pressure that the vapor exerts back on the liquid. The higher the temperature, guess what? The higher the pressure. And that's the same relationship we saw in the gas law stuff. It's a direct relationship. If it's not at equilibrium, we have gas law problems, and we're not going to do that. We're only going to talk about this in terms of equilibrium. The thing that I find fascinating, guess what happens when the equilibrium vapor pressure is the same as the atmospheric pressure outside. I'm not going to tell you. I'm going to let you puzzle on that for a sec. So, we're going to come back to the idea of equilibrium vapor pressure. Volatile versus non-volatile liquids. Have you all heard, again, colloquially, the term volatile used to describe someone? Oh, I don't know, she's got a really volatile temper. Hair trigger. They'll just start screaming at you for no reason whatsoever. Stop talking about me. But volatility is being subject to rapid change. That's how we talk about volatility. If a situation is volatile, something is likely to change at the drop of a hat. Volatile liquids evaporate at the drop of a hat. They evaporate very quickly. If we take something that has a very weak internal force of attraction, like rubbing alcohol. How many of you have spilled gasoline on your hands in the winter? Nobody? Who here has had to change, anybody, you don't wash out wheel bearings anymore, do we? Anybody here ever wash out wheel bearings? Man, I gotta start assigning that as homework. Parts washers? Okay. You've used solvents. Those things tend to be volatile organic compounds. Spilled rubbing alcohol on your hands in the winter outside? No. Okay, you need to go do that. Put sea breeze on your face? No. Wow.
You mean the sunblock?
No, I mean the like zit remover. I don't know. Teenage girls used to bathe in that stuff when I was in high school. Like, whether you had zits or not, we all smelled like sea breeze. I don't know why. It actually smells kind of nice. But it makes your skin cold. You put it on and it evaporates really quickly and it makes your skin cold. Same as rubbing alcohol does. If you spill gasoline on your hands in the winter, it will feel like your hands are so cold that they would break if you bump them up against something. The pain is so intense because they are like super chilled. It's awful. It's horrible. Horrible thing. Gasoline, rubbing alcohol, things like sea breeze, they're all volatile liquids. They evaporate really, really quickly. Non-volatile liquids have got much better forces of attraction internally. So they don't evaporate as easily. They tend to stay in the liquid phase more readily. If you actually could get salt hot enough to melt it, it would be incredibly non-volatile. Oils and greases, glycerin is one, the stuff that we used to lubricate glass tubing in labs here. If we had soaked a paper towel in glycerin at the beginning of the year, it would still look greasy. The glycerin still would not have evaporated from the surface. It doesn't come off that surface easily. Oils don't come off the surface as easily. They don't really dry up. They just kind of get sticky and puddly. It's kind of gross. Water will completely dry up. Not as fast as alcohols. Alcohols will dry up very quickly. They evaporate very readily. But that's volatile versus non-volatile. When we boil something, we get particles to leave the liquid phase from the center of the material. And they get enough energy to break free of their bonds, to break free of the surface, and escape into the vapor phase. Boiling happens when the equilibrium vapor pressure is equal to atmospheric. So, for water, at what temperature is the equilibrium vapor pressure of water 760 torr? At what temperature does that occur? I heard answers in... Okay, I'll take that. 373 Kelvin, 100 Celsius. I'll take 212 Fahrenheit, but I'll scowl at you. So, yeah, at the point when the pressure that's holding water molecules down in the liquid phase is equal to the atmospheric pressure, they all escape. They can all escape. How does changing elevation change boiling point? Okay. What we're going to do is tomorrow we're going to start off with some equilibrium vapor pressure charts, and we're going to do some practice. This is one of the skills that really, really helps you on the ACT, because we've got a series of sort of critical thinking questions. How many of you have ever seen an equilibrium vapor pressure chart? None of you, except maybe on the ACT. But if you did, you don't remember what it was because you never saw it before. So we're going to start working with those tomorrow, and we will work with those also on Wednesday, and we'll start into some phase change diagrams. That's it.